Yeah. One thing that I want to refer to here is it's a little bit like Gini. Back in the old days when we defined OSGi, it was internally at Sun it was competing a little bit against Gini. But the difference to Gini is that first of all it's designed to, based on RMI, as I said earlier, it's designed to be more distributed. And it's Gini is also, for example, here with the lookup in the filters, Gini only required you to look up things by interface. You couldn't specify any other properties, and you couldn't specify any comparisons in Gini. So that's what we fixed in this one. And the filter syntax can also be used in the applications. It's an API which is available to applications to use. Yeah, I don't really want to talk about the service tracker. It's the service tracker allows to. It's an API which allows to keep automatically track about services coming and going. It simplifies the implementation work quite a bit. So that's more an implementation tool that people can use when they implement applications on this. I've been referring to this earlier. Java applications typically consist of classes placed in packages, and Java searches for a certain class, usually in its class path, defined through the environment variable. And applications can extend the search path with dynamically created class loaders. And this last bullet item is something that most people who write Java code just overlook, and very few people use actually dynamic class loaders. But that's something that OSGi is very central, built around. So this here is, I mean, that's more or less a little Java overview again. Java programs are typically organized in different packages, and a class is always defined in the context of a package. So here, for example, we have a package called Ericsson OSGi Profiler, and we have a class X. Then this is actually called Ericsson OSGi Profiler.x. I mean, that's standard Java. Java package is an indivisible unit of a set of related classes. Okay, so I think this one is the. In OSGi, each bundle has its own class loader. And as I said earlier, typically each bundle can only access packages from its own class loader. The only way how we can share or access other packages is if they are declared as either imported or exported in the manifest. And we also have to have permission to do this. So this is again the fine-grained permission check. The framework itself manages the class load. So each bundle has a different class path when it comes to it. I mean, it's like each bundle has a default class path, which is its own jar file, and then it has all the other packages added to it, which it either imports or exports. And it assures that all bundles use the same class path. The same class is, as I said earlier, there is probably the most tricky exception with OSGi applications is the class cast exception, because I've seen many people basically making the mistake of bringing all their own classes into the application, and then you can end up in a situation where you have different implementations for classes, or even the same implementation just loaded out of different files. And then you try to assign them or compare them, and you get class cast exceptions. And you do a stack trace, and they all look the same, and it takes them usually an hour to figure this out. It's an interesting bug. And the framework tries as much as possible to prevent this, which, yeah, usually works. And it also tracks the dependence of packages between bundles. So, for example, here we have an OSGi class path, we have the standard class path of the OSGi framework, and then, for example, one of the standard services, which is here the OSGi service HTTP. And then bundle A might actually bring a log service and export the log service. It also might bring an implementation of the log service, which is here the IBM log service, and it might bring some classes for IBM J9. It, in this case, imports the HTTP service and the JavaX servlet HTTP. Most of the classes, for example, here the HTTP service can be loaded through the framework class loader from this package here. Now we have a bundle B. So the problem with this one is that the JavaX servlet package, for example, was not available because bundle A tried to import it, but the framework did not export it. So the bundle A could not be started. Now after we install bundle B, which exports stuff like Ericsson OSGi, but also javax.servlet, now we see that this dependency can be fulfilled, and JavaX servlet HTTP is exported by bundle B and imported by bundle A. So bundle A is now, as we saw, say, resolved. It has all its dependencies resolved and it can be started. And bundle B, so we continue linking this a little bit further here. So now bundle B basically gets all its dependencies resolved, for example, from an export from bundle A. And then bundle B is also ready to run and could be started. So those are the dependencies that the framework kind of keeps track of. Yes?
Going back to the life cycle of a bundle, when you stop a bundle, but another bundle has done a get and they, let's say, didn't do an unget, can you uninstall if another bundle is already?
Okay. So there is a few cases. So there is the one case where the two dependencies is a package dependency and a service dependency. So what you referred to was the service dependency. The service dependency, if a bundle does not give up a reference and it does not unget the service, it's actually even more drastic, because when a bundle does a get, it gets an actual object from the framework, which this object has been instantiated from the class loader of the bundle that registered it. Now this object you can call methods on, you can do whatever you want on it, as long as somebody has a reference on this object. And for example, bundle A registers it, bundle B gets it, bundle B now has a reference because it's sitting somewhere in a variable, it has put it in a hash table or done whatever with. As long as there is a reference, a Java reference to this object, bundle A can go away and it can stop working, but the problem is the class loader cannot be garbage collected. And this package cannot be garbage collected because the VM only garbage collects when the last reference was given up. So bundle B has to voluntarily give up the reference. And so typically what you have to do is you have to, for example, when you assign it to a variable, you have to just override this variable with a null pointer to make sure you have given up the reference. And then you inform the framework and you say, okay, I have given up the reference, and then the framework will start the garbage collection. So that's the unget. Unfortunately, if you have either maliciously or out of, having a bug in your software, you call the framework and you tell the framework, yeah, I've ungotten this, but you actually still have a reference somewhere deep down in your code. The framework will try to do a garbage collection on the class loader and on the package, and it cannot garbage collect it. So this would be the case when you actually have a memory hole. And unfortunately, we've tried various things, but there isn't really anything that the Java VM allows you to do, because we would basically have to we would have to change the garbage collector implementation of the VM to allow to withdraw, basically forcefully withdraw objects that still references exist, and then maybe next time you use the reference you would just get like an invalid pointer exception or something like this. but unfortunately Sun wasn't very cooperative changing the VM.
Have you looked at the upcoming application isolation
No.
information?
No.
I can tell you more about it.
Okay. Good. Yeah, I mean, one of the things how we tried to solve this was if you would use RMI. So that's unofficial here, but what we tried to look at in our labs was to just basically use RMI and create proxies so that you don't hand out the real objects, but you just hand out a proxy object and they interact with RMI. Then you could actually destroy all the packages and all the class information, and you would just have this proxy hanging around, and you would limit this problem because you have like a separate interface. Yeah, so the package handling here, the package admin service, this actually implements the policy of the package handling. It does the uninstalling. As it says here, uninstalling a bundle will not withdraw export packages anymore. This is another case here, because what I was just saying is the service dependencies. Now the differences with package dependencies, because there, when you export a package and somebody else uses this package, like you instantiate classes out of this package, then what happens is you can't undo this because the classes are around. Even when you try to uninstall this package, you can't force everybody else to give up those instances that they have created. And we have changed this now. In version 1, it was said that you have to be able to withdraw this, but this caused major confusion. So in version 2, the packages will not be withdrawn. They're just around until somebody uninstalls the last bundle. So it's a compromise between really confusing people that implement software and saving memory. Well, it also keeps track of the IM and exporting from the manifests, and it cleans up stale exported packages by stopping and starting the minimum set of bundles. That's an optional feature that allows you to more or less garbage collect bundles that haven't been used. Native code, well, we have, as I said initially, we can include whatever native code we want in a jar file, as long as we know that the platform that it's deployed to supports the native code. The matching of the operating system, processor, and language is actually supported by the framework. So we can have different bundle versions that specify in the manifest different operating systems and processors, and then only the ones with the matching operating systems get installed. The life cycle, as I said, is life cycle of native code is bound to the life cycle of the bundle, which makes it even more difficult because you must really clean up after your native code. And it requires Java 1.2 native code support. So the initial pjava implementation didn't have this, but then there came another pjava implementation that had the Java 1.2 native code support, and it had the 1.2 security support. So that's what we run on. Well, that's how to use native code.